Previously, we talked about acid analyte and phenacetin, and we said that your unknown in this lab is going to be one of these two things, right? It's either going to be acid analyte or it's going to be phenacetin, and we've got to figure out how to determine which one this thing is. Okay, so how do we do that? Well, the lab directions are going to kind of walk you through it. So in the beginning, like we said before, it's your job to separate the three components. All right, so what does that mean? Well, let me just kind of draw it out if I can. So in the beginning, you're going to have a three-component mixture, and I'm going to use three different colors here. And one of these, and I'm going to say the green one, is going to be phenacetin, and I'm just going to abbreviate it, or acid analyte, and I'm just going to abbreviate that one as well. And I've got to figure out which one it is. Well, here's the thing. I know that these two have different melting points. Hey, if I can do a melting point, I can determine which one it is and maybe feel good about it. The problem is that if I take the sample as it's given to me, I can't do a melting point on that because it's a mixture. There's more than one thing that's present. And if I do it, it's not going to make any sense. All right? So the first thing that we're going to have to do is that we're going to have to take the sample that's provided, and I'm going to have to go through and I'm going to have to separate out the different components from each other. And that is the purpose of experiment number 2, the very first one that you do. Okay? So the very first one will separate these things out into the clean individual components, and then we can do testing with them from that point on. Okay? So once I do this, I will have an isolated unknown. And now I can do the melting point in order to determine which one it is. But I have to make it to that point first. All right? So that comes a separation technique. So the separation technique is going to be played off of the solubility. The solubilities are all different, right? Remember, sugar was very soluble in water. The other components, though, not so much. They had a tendency to not dissolve in water. If it was hot water, it was a little bit better for them. But just simple, normal, regular tap water, no, it's not going to happen. So in the lab directions, it's going to say step number 1, add methylene chloride. Now, methylene chloride goes by a different name, and that name is dichloromethane, abbreviated as DCM. Okay? So what is methylene chloride or dichloromethane? Well, dichloromethane is a carbon that has 4 bonds, like all carbons. 2 of these are going to be hydrogen, and 2 of these are going to be called chlorine. That's why this name is dichloro. Di meaning 2. So dichloromethane. It has a common name, methylene chloride. And it also has an abbreviation, D for di, C for chloro, M for methane. So that's a solvent that we can use. So here's the good news. Step number 1, it says add methylene chloride. Well, we've got this 3 component. This is sugar. Sugar does not dissolve in methylene chloride. But all of the other components that I need to separate, it does. So what I can do is I can take a beaker or a container and I can put my mixture here in the bottom, and then I can add my methylene chloride, my DCM, into that beaker, and I can stir it up. And everything in here is going to dissolve except for the sugar. The sugar will stay as a solid. It will not break down. And then I'm going to pour that solution through a funnel. And when I pour that solution through the funnel, all of the liquid that goes down below, this is what I'm going to keep, because now it has 2 components in it. I'm going to have some solid crud that's left off in the top of the filter flask. And that solid is going to be my sucrose. So I will take that solid and I will dry it. And when I let it dry, I evaporate all the water off of it to get rid of the weight. And then I'm going to weigh the amount of sugar that I have collected. And that weight, depending on my starting weight, I can calculate a percentage, and then I can report that percentage to see if it's correct. Okay, so that's step number 1. That's the first part of the procedure that you're going to be doing. Add methylene chloride or DCM. It separates the sugar since it will not dissolve, but all the other components will. Step number 2, depending on which edition of the lab manual that you have, is going to be salting out acetyl salicylic acid. So if you've got the 4th edition, it's going to tell you add sodium bicarbonate. If you've got the 3rd edition, it's going to tell you to add sodium hydroxide. Either one of those are okay. So you're going to add sodium bicarbonate or sodium hydroxide. And this forms a salt that will precipitate out of the methylene chloride. And it's a salt of acetyl salicylic acid, aka aspirin. All right? So when I separate those two components, I've got these two down here in the beaker. Now I need to separate those two from each other. So what I do is that I add the hydroxide or the bicarbonate, whichever one that the lab book tells me to do. That's the one that I'll do. And when I do that, my beaker solution's going to be there, and I'm going to see some solid that begins to fall out in the very bottom. And this solid, I'm then going to pour through a filter yet again. And I've got my liquid down here at the bottom. And then that solid is going to be up here at the top. And this is the aspirin. I'll do the same thing. I'll let it dry. When it dries, I'll do a weight. I'll use that weight, compare it to the starting weight of the entire thing from the very beginning, and I calculate a percentage. I've now separated my second component. Okay, so finally down here at the bottom of the beaker, this is where my third component is going to be. And this third component is either acid analyte or phenacetin. I've got to figure out which one it is. But I got to get it to a solid first. So in step number 3, we're going to evaporate the DCM off. The liquid disappears, and you'll have the solid that's left behind. Okay? So that means in this step, I'm going to put this on a hot plate, crank up the heat a little bit, and allow the hot plate to drive off the methylene chloride fumes. And when all of that gets driven off, I'm going to be left with a cruddy, solid residue in my container. Now, the methylene chloride, you probably don't want to breathe it in. So we encourage you to do this under the hood. Whenever we evaporate solvents, if they're organic solvents, we encourage you to do it underneath the hood when you can. Okay? All right, so some pictures that maybe I want to show you before this video stops. Here's a picture of the fluted filter paper. The lab is going to say, flute a piece of filter paper. If you really want to take the time to do it, this is what the fluted filter paper looks like. I think that it's actually kind of silly. I don't really do it that often. I just basically do the half moon folding, and the half moon folding is basically take a piece of filter paper, fold it in half like a taco, and then fold it in half again, which will give you a quarter. And this is typically where I stop at this point. I open this lip up, and I put it into the funnel, and I filter things through it. However, fluted takes it a step further. It will then take this quarter, it opens it back up, so you got your taco again, And this time they will take the out and fold it inwards to divide that up into, again, smaller pieces, like a pizza slice, right? And then they're going to do it again. They'll take that and then fold that little piece in half, and then take this end and fold that little piece in half. And then they get this accordion-shaped filter paper. They will then grab a hold of the center, and they will push everything upward, and they get this open fluted filter paper to use in a lab. If you want to take the time to do it, you're more than welcome to do it. But we just think that this is really a waste of time because we don't think that it actually filters things out any quicker at all. Okay? Notice in the second step, we talked about the aspirin salting out. So what does that really mean? Well, here's the structure of aspirin. It's just drawn a little differently for you in this slide. And if we add sodium bicarbonate or sodium hydroxide to it, what does it do? Okay, well, remember, this is a negative area of the molecule, just like sodium benzoate was, right? This O and this OH group has some negative charge. Well, sodium hydroxide or sodium bicarbonate, that carries a positive charge. It's a salt. This is a full-blown positive, and this is a full-blown negative. So that positive piece is going to come over and it's going to hang out with this area, and that forces the hydrogen to kick the curb, right? And when that hydrogen kicks the curb, off it goes, and it kind of binds up with HCO3, in a way making H2CO3 that then gets broken down to CO2, which will be bubbles. So if you see bubbles in the lab when you do this, that's where they're coming from. But this is what we would call soluble aspirin at this time. It's the removal of that hydrogen, and it's adding on a sodium. And this creates a full-blown positive and negative charge. And whenever we see something like this, that means it will dissolve in water quite well. So we've changed the solubility by salting it out. We've incorporated a cation that has attached itself to the molecule that has a full-blown positive-negative that can come out of solution or stay in the solution depending on what kind of solvent that it is. All right? In this case, methylene chloride is nonpolar. So when this thing becomes polar, like it is here and over to the right, it's going to fall out of solution and it's going to precipitate on the bottom of the beaker. And that's why it does that. In the lab, you're going to use a separatory funnel. The separatory funnel allows you to separate two liquids from each other. So the liquid water layer and the methylene chloride layer, they do not mix together. The methylene chloride will contain the unknown that you need for part 3. And then the aqueous layer will contain the aspirin that you will need for part 2. Okay? So here's a real picture of a separatory funnel to the left. On the center, it just kind of tells you what's going on. You're going to have 2 layers. You need to separate them from each other. So make sure that you don't have a stopcock up here or a lid onto the top of the sep funnel. Open up the stopcock, allow it to start draining into this receiving flask that sits down below, and then stop the drainage when your layers begin to get to the meniscus line of the stopcock. All right. A lot of people, they'll grab a separatory funnel in our lab and they don't really know the proper way to thread them. If the stopcock, or what they call the valve here in this diagram, is not attached for you, you need to put the plastic or nylon ring on first. Then the rubber O-ring goes on second, and then the nylon or plastic nut goes on third. That's the proper order to attaching a stopcock at the bottom of the sep funnel so it doesn't leak on you. And you can kind of see this at the diagram down below, right? Here's the stopcock area. You see the plastic piece, then the rubber O-ring, and then the little turny valve or the nut that you put on afterward. Recrystallization, the lab's going to require you to recrystallize. So that means take the sample for experiment number 3. You're going to take this crud, this solid that you have left now that you've evaporated the DCM, and they want you to recrystallize it, which means they want you to add solvent and they want you to take it back into solution. They want it to dissolve again. And then they want you to basically drop the solvent off one more time. Just give it kind of a rinse. Think of it as a shampoo and rinse in your shower. This is the rinsing step. That's recrystallization. I've got this product. I want to make sure it's clean. So therefore, I add solvent to it, redissolve it, and then I bring it back out of solution in some form or some fashion. So in this experiment, the unknown components are soluble in hot water, but not in cold water. So with this, the only thing that we have to do is take this crud or this residue that we get from the experiment number 2, and we're going to add water, put it on a hot plate, we're going to heat it up, get it hot, and it will dissolve it. Then we turn the heat off and we allow it to cool. And as it cools, that solid will begin to precipitate out of solution because it's soluble in hot water, but it's not soluble in cold water. Here is a recrystallization before and after. So you can easily see that the recrystallization steps really do make a difference in the product formation. This is the crud product to the left, or the crude, and I call it crud because most of the time it is crud. And then recrystallization will allow you to get crystals like you see over here to the right-hand side. This is the same material, the same compound, but recrystallization completely takes away the impurities. It allows the crystals to form much better, and you'll see a big difference in your physical property test when you do recrystallization. Here's another before and after recrystallization. Never really assume that every single time that you will start off with a solid, because sometimes you won't. So here we've got basically a liquid, and this liquid is going to get recrystallized. So we're going to put a solvent in it, then we allow it to come back out of solution, and when we do that, we end up with a white powder that's kind of fluffy. It's kind of strange to see that happen, but again, there's so many impurities here that it's hanging on to that it's turning into a liquid and it's keeping it that way. All right, so in conclusion, what you will need to do, number 1, determine the amounts of each component present in the sample provided. You need to determine the milligrams or grams of sugar, aspirin, and your unknown that you have. And everybody's will be different. Number 2, calculate the percentage based on your sample weight. Is it 30%? Is it 40%? What is it? Number 3, does it match the company's criteria? So that means the lab told you what should be present. Are your percentages anywhere near it? Yes or no? Number 4, identify the third component by melting point. That's basically going to be experiment number 3. So once you recrystallize, you're then going to go do a melting point, figure out which one of the 2 it is. Number 5, could it be acetaminophen? Maybe we've played a trick, and maybe that compound is neither one of the 2. And maybe it's just simple old Tylenol. So is your melting point closer to Tylenol and not acetaminophen or not phenacetin? If so, then not a problem. You know what that melting point is now. And number 6, determine what it is if it's not acetaminophen. So again, you've only got 2 choices. You got a 50-50 shot of getting it right if it's not acetaminophen at all. All right, so I'm going to pause the video here. In the next one, we're just going to finish up and we're going to talk about drugs since we're on this market. It gives me a very good time to talk about the drug industry. So come back, take a quick breather, and then we'll talk about drugs and drug recalls and what to watch out for.